Hi everyone, so now we're going to be talking about exponential growth and decay models. We've already learned about the discrete model last year. It's the y is equal to p times 1 plus or minus r to the power of t, which is the first equation that I have right here. But these other equations are new, and so let's just go through all of them really fast. For the discrete model, it's the y is equal to p times 1 plus or minus r to the power of t, where p is your starting amount, and r is the rate of increase or decrease, and then t is the time. So in this formula, you're looking for you have to decide if it's a plus or a minus. So if it's growing, then it's plus. If it's decaying, then it's minus. And then you can just plug in all of your values. The other thing to recognize is that your r will always be a percent, but you have to write the percent as a decimal. So for example, if it was like 7%, then the decimal would be 0.07. And we use this discrete model when it gives us very specific numbers and it doesn't tell us it's continuous. If it tells us it's continuous, then we have to use one of the bottom three equations. So let's go through these bottom three equations. The first one is the continuous, which is y is equal to p times e to the power of rt. So p and r and t are exactly the same as the first one. P is your starting amount, r is the rate, it's a percentage as a decimal, and then t is your time. E is a number on your calculator. This is something you can find on your graphing calculator. You can use desmos.com/scientific. It'll be on there too. It's usually on a graphing calculator, the same button as the LN button, which is down on the bottom left. And you're going to use this formula when it tells you that it's a continuous growth or decay, but that but it also gives you a percentage. And the other thing too is this r right here. So we decided it's a rate, which is that percentage. Now if it's growing, it's positive. So growing is positive. If it's decaying or if it's getting lower, then it's negative. And you just make the r positive or negative based on that. Okay, then we have these other two equations. The first one is the doubling equation. So it's still going to tell you in these word problems, it's still going to tell you that whatever is growing or decaying exponentially, but instead of giving you a percentage, it'll say that it's doubling. And so when it's doubling, we use this formula where p and t are the same thing as normal. P is the starting amount and t is the time, but now you have this letter d, and d stands for the doubling time. So it'll always tell you that it doubles. Whatever's happening is doubles every so many years or so many minutes or so many days. And so that's what you use for d, is how long it takes to double. And then the half-life equation is basically the backwards version of that, where instead of doubling something, it's still continuous, but it'll be halving something. So p is your starting amount, t is your time, and then instead of having a d, instead of dividing by d, you're going to divide by h, which is your half-life. It just tells you how long it takes to get to half of that value. Okay, and you have a paper with all of these formulas on there. Let's get started on the examples. So I'm not going to write down the examples because you have them in front of you, but I will write down the important stuff. So for example 1, an employee receives a 4% raise once per year. If the employee's initial salary automatically clues me in that it's a P, or a starting amount, is $71,300. And what is the employee's salary after 5 years? So, okay, that's a time frame, so we're going to say T is equal to 5. All right, because it didn't have that word continuous in it, we're going to use the first equation, that discrete model, y is equal to P times 1 plus or minus r. And because it's growing, it's a raise, so you're getting more money every year. Instead of using minus, we're going to use a plus. And the only thing we don't have is your r, because we didn't talk about it, but that percentage is your r, but we would write it as 0.04 because we want to write it as a decimal. Basically, if you have a hard time with this, you take your percentage, so 4%, and always divide it by 100 to get your decimal, which is what happened there. Okay, so when I plug all of those values in here, I get y is equal to p, which is 71,300 times 1 plus 0.04 to the power of 5. And I'm just going to plug that straight into a calculator. So 71,300, 1 plus 0.04 to the power of 5. And I'm going to get that y is equal to $86,747.35. So that's how much money we would have after 5, or how much money we'd be making after 5 years if that's the raise we received. All right, let's look at the second example. So the second example says atmospheric pressure decreases approximately exponentially. Okay, it says the word exponentially, so that clues me in that I'm going to use one of the bottom 3 equations that we talked about. As elevation increases, if the continuous rate of decrease is determined to be 19%, so we know it's a 19% decrease. Oh my goodness, spelling is not my strong suit. Per mile, and the pressure at sea level is 31 mmHg. What is the pressure 6 miles above sea level? So this one's a little bit harder to decide what one the starting amount is, but it's going to be the pressure at sea level. So that is 31 mmHg is my starting amount, which is our P. And then it's asking what the pressure is 6 miles above sea level. So that's not necessarily a time, but we can use this as a time, so we're going to say that 6 is equal to t. Now, here's the deal. In this equation, we're going to end up using y is equal to p-e-r-t. The reason why we use this equation rather than the doubling or halving equation is because it didn't tell us it doubled or halved, it gave us a percentage. And that percentage, that 19% decrease, to write it as a decimal, I'd have 0.19, but because it's a decrease, I'm going to make it a negative 0.19 when I plug it into the equation. So when we do the equation, we're going to have y is equal to p, which is that 31, times e, and remember, e is just a number on your calculator. You don't have to replace it with anything, to the power of r, which is the negative 0.19 times t, which is 6, and then we're going to plug that into a calculator, which gives me that y is equal to 9.91, and that is in millimeters of mercury. So that makes sense because we decided it was decreasing, and we started with 31 and it went down to 9, so yeah, it did decrease. All right, let's go through the third example. On the third example, it says, for a period of time, an island's population grows exponentially. Once again, it says exponentially, which clues me in that we're going to have to use one of the bottom 3 equations. If the population doubles every 34 years and the current population, okay, so that tells me that the doubling time is 34 years. And the current population, is 1,426. What will the population be 4 years from now? So this should kind of already clue you in. Because it says the word doubles, we're going to use that doubling formula, which is y is equal to p times 2 to the power of t divided by d. Now it tells us the doubling time because it says it doubles every 34 years. And it tells us the initial population, which is that p. It also tells us that we're looking for what's happening at 4 years from now. So that's our t. So when we plug everything in, we're going to have y is equal to 1,426 times 2 to the power of 4 divided by 34. Make sure that both of those things are in your exponent. So when we plug that into a calculator, we're going to end up with that y is equal to 1547.1. And because it's people, we're going to round that. So it's just 1547, or 1,547 people. There we have it. Okay. And we have one more example to work through. So this example says, a cup of hot coffee is placed outside where the temperature is 0 degrees Celsius. Assume the coffee cools to approach the outside temperature according to an exponential decay model. If the temperature in degrees Celsius decreases by half every 23 minutes and the current temperature of the coffee is 53.8 degrees Celsius, what will the temperature of the coffee be 8 minutes from now? So it tells us automatically, it says something about half. So we're going to use that halving formula, which is y is equal to p times 1/2 over t, or to the power of t divided by h, where p is the starting temperature of the coffee, which is 53.8. And then t is the amount of time we're going to wait for it to hang out, so that's 8 minutes. And then your h is how long it takes to cut in half, which is that 23 minutes. So now let's plug everything in. We're going to get y is equal to 53.8 times 1/2 to the power of 8 divided by 23. Once again, the 8 and the 23 are both in your exponent. And when we plug that into the calculator, I'm going to end up that y is equal to 42.27, and that's in degrees Celsius. So after 8 minutes, it cooled down to 42 degrees Celsius. There we have it. This is how we use exponential growth and decay models.